Can you put it? Okay, perfect. Thank you.
All right, let me know when I'm good to go.
You're good.
Okay. Hello, good morning, good afternoon, everybody. My name is Anthony Hirika. I'm a systems engineer based out of Austin. And today, along with Rocky Song, he's based out of China, we're going to be talking about the brand new EIQ Neutron module. And so we're going to talk a bit about machine learning basics, just as a refresher, and how and why this new module works with increasing the or decreasing the inference time when doing inferencing of a model, and then go into a bit of the details on Neutron, the Neutron enablement, and then some time for Q&A. So I wanted to start this morning actually with a song. So some of you might have heard about this new AI chatbot that's been in the news and all over the internet the last few days. And so I asked it to write a song about microcontrollers. I'm not going to sing it for y'all, but this is just to get an idea of what AI is capable of now. Obviously, this is not on a microcontroller, but it does show, how there's these constant advances in AI happening all the time that then trickles down into the embedded world. I also decided to ask it to help with this presentation. So if you remember our agenda, this actually created basically that same outline, how we're going to talk about ML, we're going to talk about specific technology and tools, and then in the hands-on that we'll have in February, we're going to go practice applying this machine learning algorithms to real-world problems. And something that, again, not directly applicable to the Neutron NPU specifically, but, using AI for code development. You'll notice that, it can create some code for initializing the LPU art for an iDynamics RT device. If you look closely at the code, though, you'll notice that it's not quite correct in all ways. It won't actually totally initialize your LPU art, but still quite impressive just to type that in and get that code back, as well as suggestions for debugging a bus access fault. So again, I'm showing this, not just because it's a fun way to kick off a Wednesday morning training, but also just to show how quickly the AI world moves. All this was released just 2 years ago, or sorry, 2 weeks ago. And while we launched EIQ, now, I think it's been over 2 years, we've already seen big changes in what's possible to run on embedded systems due to advances in model design and optimizations and accelerators. And so the NPU that I'm going to be talking about this morning is just another step forward in this evolution. And it's not a static field. It's not like most modules on a chip where you either have BLE or you don't, and then you're going to support BLE or it doesn't, or you have a UART or you don't. What's possible and what you can do is constantly changing. And so it's still a very exciting field to me. So machine learning kind of works with being able to create new rules to handle data. So in traditional programming, you as the programmer have to think up rules and then take in data, and then hopefully the rules that you wrote, the program that you wrote, will give you the correct answer. With machine learning, what it does is it takes in all the answers as well as the data and then creates rules. And then those rules can be applied to new data, and hopefully you'll get the correct answer for that new data. You can think of it how would you create or write a program to identify a cat in a photo? If you had a single photo with a single cat, maybe you could, think of some rules as a human of like, okay, well, it has 4 legs and it's got a, this cat-looking head, and it's, black and white. But then if you had a second cat photo, where is a tabby cat that's, orange and maybe it's lying down. And then if you had a third photo with, maybe it's facing away from you. And then, well, what happens now if you want to figure out what a dog versus a cat looks like? Well, they both have four legs, they're both furry. How do you determine that? And so if you're a human trying to program all this, it gets very complicated very quickly. Whereas with machine learning, you just show it a whole lot of photos of dogs and a whole lot of photos of cats, and it'll automatically create those rules. And so what those rules look like in an embedded or a machine learning neural network is as different nodes and layers and a neural network model. And so basically you take the input, which would be like the pixels of an image or the sensor data from your accelerometer or the frequencies of different sounds. And then you're going to multiply those input values by different weights, and then add or subtract a bias, and then you'll get one of these internal nodes. There's my pointer. One of these internal nodes. And you're going to do that a whole lot of times. So this is a very simplified diagram of what a neural network model looks like. Right now we have, showing this image, we have like 4 nodes, but in a real neural network model, you could have dozens, hundreds, thousands, tens of thousands of these nodes. And for each one of these nodes, you're going to take the value, you're going to multiply it by a weight, and then subtract and add a bias. And this is really important because you'll see that this is just a basic multiply and accumulate. And so because you're doing this multiply and accumulate thousands of times, if you can accelerate that math, then you can decrease the inference time for running your model. Because at the end, after you do all those multiply and accumulates for all these different internal layers that have different operations that they're doing, then at the end of the day, or at the end of the inference, then you're going to get an output value. And whatever node has the highest value, that's what that model thinks it is, whether it's a cat or a dog in this simple example. And so that's what I want to impress upon everyone this morning, is that ML inferencing, running a model and analyzing a photo or a sound or sensor data, is mostly just doing millions of multiply and accumulate math calculations, which pretty much any MCU or NPU could do. There's no special hardware or special module that's required to do this inferencing. But if you have specialized ML hardware accelerators, like the Neutron NPU that's found in the MCX, then you can drastically reduce that inference time. And so probably the most common question we get is, how will this model run on a particular device? What can this device support? And it's extremely model specific because it's going to depend on how long does it take that inference to run, because that same model is going to take longer to run on a less powerful device. And the maximum acceptable inference time is going to be very application dependent. So if you're in a coffee maker trying to determine how roasted the beans are, as we have in a demo in our smart home lab in Austin, if it takes 1 second to do that analysis, that might be okay. Because you're standing at a coffee machine, it's going to take a while to brew the coffee anyway. So a second lag isn't going to be necessarily a deal breaker. Versus if your application is a car driving at 70 miles an hour, then you probably are going to need to determine if there's a couch in the middle of the freeway that you need to avoid, that someone actually dropped, faster than 1 second. So it's very application dependent. The second consideration is there enough flash memory to store the weights, the model itself, and the inference engine? And is there enough RAM to store the intermediate calculations and the output? And so all 3 of those combined are going to determine what kind of model can be ran on a specific device. And for the MCX with the neural network processing unit, you're going to significantly decrease that inference time. And Rock will show some benchmarking on that there at the end. So the other key concept is that is understanding that many different model structures can be used to accomplish the same goal. And so determining the best model for a particular application can require some experimentation. You can have an extremely complex model that determines the color of if a shirt is red or blue, but you can also have a simple model that determines if the shirt is red or blue. Both will work perfectly fine, but obviously typically the best model is going to be the smallest model that can do that particular application. And that application does have a large effect. So, if I'm on a factory line, just have a camera determining is this shirt red or blue, that can be a much simpler model than if my goal is to identify four-door sedans in a variety of different locations and lighting and weather conditions. Determining the difference between a Toyota Camry and a Honda Accord is going to require a significantly more complex model, even though technically you could say, well, they're both doing image classification. So that's what makes this whole field kind of complicated, is determining what that minimal model is that can still accomplish your goals for your application. And there's always this trade-off of trying to spend more time creating a better, more efficient model versus just throwing hardware processing power at it, and being able to develop more quickly. So it's, do you want to spend money on, or for a customer, it's, do they want to spend time and effort to develop a better model and hope they can squeeze it into something like an MCU, or they just go with like an i.MX because they know it'll work, but at the trade-off of an increased BOM cost. And so with this neural processing unit, the idea is that, at least from the inferencing side, power consumption side, it makes it much more attractive to run these models on an MCU. I also want to point out that the official name for this module, or the marketing name, is EIQ Neutron. So the Neutron you might have heard of as the code name for the development of this module. For branding purposes, it is officially called EIQ Neutron, to ensure we have naming rights. So what does this look like? So it's a module specifically designed to accelerate neural network matrix computation to reduce model inference time. So if you recall from a few slides earlier, the vast majority of calculations that a model is going to be making as it does its inferencing is these multiply and accumulates. And so just like a DSP can speed up signal processing math that you want to do, or a floating point unit can speed up floating point math, this neural processing unit is specifically designed to speed up the math that's done when you're doing inferencing of a neural network model. And so there's three main components: weight decoding, a compute engine, and a data canvas, which is basically just a data buffer for storing some of the internal calculations. There's multiple parallel multiply and accumulate blocks. It has weight decoding, but it's assuming that the weights are going to be quantized, and a built-in cache. And one of the common questions you get when you start talking about neural network accelerators is, well, how many tera operations or giga operations can it do per second? It's kind of a rough guide of how powerful one is. So for the Neutron version on Nirvana, we have 16 max per cycle. It's doing 2 operations at 150 megahertz, which is the core speed, giving us 4.8 GOPS. So it's this is an NXP developed module, and it's been optimized for performance and power efficiency. The reason that we went with an internal development of this module rather than using one of the ARM accelerators, because you're very likely to get asked about that, is that it gives us better flexibility to tune for particular devices to scale up and down our portfolio. So the ARM neural network accelerator would be far too big for an MCX class device. And so this allows us to keep the same enablement and same software up and down our entire NXP portfolio. And I'll show a roadmap near the end that shows where we plan on taking this. So this is not a one-off device or module. This is going to be put into a lot of upcoming MCX devices, iDynamics RT devices, and iDynamics devices. So the key software enablement is this new converter tool. And so the way that it basically works is that you have your model, and there's all these different types of nodes in it. And the converter tool will analyze the model and then converts the compatible nodes into a quote unquote neutron node. And so this is a node that's been optimized for our NPU. Not all nodes will be able to be optimized, but the more nodes that can, then the faster your model is going to run. And you'll see that in some of the benchmarking data, where the acceleration achieved, it can run 2x faster, 10x faster, is going to be very model dependent. And part of the upcoming enablement and documentation is how to optimize a model for that. We'll talk about that here in a little bit. But what nodes it can, it's going to group together and make into a neutron optimized node. And so it'll have, you basically just taken your model that you've already created and then export it as a TF-Lite file, but that's been optimized with these neutron nodes for the NPU. And this is what the training in February will cover in a lot more detail. But this is the basic idea. Once you have your neutron converted model, then you would just drop that into your application that's running on the M33 core. And from a user point of view, there's not a whole lot to it because you're just dropping it in as we have these examples already in the SDK, and so you just replace the default model with your custom model, and all the actual hard work is going to be happening in the background. And so whenever during the inferencing phase, our EIQ TensorFlow Lite Micro inference engine will identify when it can offload operations to the NPU, and it will run that on the NPU. Anything that can't be run on the NPU will just be run on the CM33, just like it would with the NPU doesn't exist. And so again, the more operations that can occur on the NPU, the faster that inference time will be. As far as naming, so we wanted to be able to differentiate between the different types of NPUs on the different NXP devices because they're going to have different features, different speeds. And so we wanted to be able to make it somewhat clear if you're comparing NPUs on our different devices, which one's going to be the fastest. So we start off with N for neutron, and then there's a series designator. The higher the number, the more complex the NPU, and therefore the faster it should be. And then there's a dash, and then the number of max per cycle. So the one on MCX is the very low end at only 16 max per cycle, but it can go up to 1,024. And then optionally, there's what we call system level components. And so this is a RISC-V core that can help offload some of that work that the core would do during inferencing. The MCX does not have this, but it will be coming on future devices, specifically mostly on the iDynamics devices, just because it does take up quite a bit of gate count. So the N1 series is the first one, and first used on this MCX device. And then we'll have the N3 series MPUs coming for iDynamics 95 and RT700 and more to come. And at some point, we'll have N5 devices. And so the way you describe this is that the MCX microcontroller has an N1 series EIQ neutron NPU core capable of executing 16 MAC instructions per cycle. And so this is what the roadmap kind of looks like. We can see our first one here with the N116 on Nirvana, and then we'll have one on an N364, meaning it's a 3 series, so more complex. capable of faster processing, as well as 64 max per cycle on the RT700, and going up for the i.MX family. One of the other advantages of our architecture for the NPU is that you can group them together. So you'll see at the top right, you have basically 4 neutron 256s combined to give you the 1024 max per cycle performance for these devices. So this is a bit subject to change, but just to give you an idea that this is not a one-off module. You will be seeing this again, and we do see it as a key feature going forward. So a bit more details. So the clock speed is configurable to balance inference time with power considerations. So if you turn this on, it's going to add about 9.5 milliamps to your current, which is quite a large percentage. If you think about that, running a core mark is like 27 milliamps. So it does add quite a bit. But if you look at the active state versus sleep state for the CM33, it's about 13 milliamp difference. And this is essentially, doing a bunch of core or math calculations. So it's, like a very powerful processor kind of thing with doing those calculations. So it's somewhat expected to see quite a bit rise in power consumption when just turning on that module. The key thing, though, is that because the inference time is going to take so much less, you end up saving a ton of power. So instead of having to take 500 milliseconds to run your inference, the CPU clock has to be going the entire time. By using the NPU, you can do that same calculation in 10 milliseconds. And so the amount of time they actually need to be awake and actively running is significantly lower. And so you end up saving a ton of power. Obviously, if you're just doing this in a loop and just constantly doing inferencing, then that's going to kind of negate that power savings. But if you only need to do a inference, once every second, or only whenever there's some sort of, it detects something in front of it, maybe with an IR sensor, and so then you want to turn on the camera, you want to turn on the model and run an inference of whatever you just stepped in front of the device, then you can save a significant amount of power. The other key thing to know is that this block is basically being presented as a black box to customers. If you look at the NPU chapter in the reference manual, there is not a lot there. It's basically just a high-level overview of the features of it, more of a marketing, like, hey, this is what we can do and speed up, rather than details on how to use the module. There's no register map, and this is all as a competitive kind of situation of where we want to keep this proprietary. And as I mentioned before, there is a model development guide to optimize models for the NPU that's under development. So that way, as customers know, okay, if I structure my model this way, then I can take more advantage of this NPU features. And again, this was done with designing our own NPU to better enable scaling up and down the NXP portfolio. As far as how it's connected in the system, there's 2 buses that it's going to use for data and operands or operators. And all this really is just controlled by the EAQ software and how it's put into the linker file. So it's not something that, as a customer, you should really have to deal with or think about, because again, you just drop the model, the converted model, into our EAQ examples, and it'll take care of everything else. But basically, it's going to be reading in the weights and biases and everything from read-only code, and then there's a data bus for RAM for all the scratch operations. Now, as far as EIQ neutron enablement, there's not a whole lot difference other than the conversion tool. Hopefully you've seen this EIQ slide. That's kind of all staying the same. The focus, though, for the NPU is going to be the TensorFlow Lite for microcontrollers. At the moment, there's no plan to enable Glow for that, and Glow is kind of going to be status maintained going forward, or it's not going away, but there's not going to be new updates for the Glow compiler tools, because all the development team and focus is on the new NPU. And so this tool to convert the models will be developed as part of the EIQ toolkit. So we should have a command line version that'll be used for the hands-on training that'll be available. And then it'll be integrated as part of that EIQ toolkit as a GUI that'll be available at the MCX launch. And there's no cost for these tools as usual. And as I mentioned, it'll use TensorFlow Lite for microcontrollers. And just as FAEs and DFEs, you want to make sure to use the release highest optimization compiler settings when you're running this code, because it does make a difference in inference times. And we found that MC Expresso and Kyle generally, but not always, have the best inference times. The other key point I want to make is that while the NPU significantly decreases the inference time, it doesn't add or enable any new features at the application level. So there's nothing that this module now allows you to do that you couldn't do before on an iDynamics 1060 or 1170 or any of the other microcontrollers. It just does it faster. And so this is important if you have a customer that might already have a ML project that they've created or that they're interested in, but they don't have an MCX device, or even going forward if they're like interested in RT700, which we don't have yet, but they want to start model development or model testing. They can do all that on our existing devices, and then once they get the NPU or the device with the NPU, then it'll run pretty much the same. The software will look the same because you're just dropping that model in and getting your result. It'll just run faster. So I want to make sure everyone understands that. I think this is something customers don't sometimes understand because they think, oh, I need an NPU to do any sort of embedded ML, and so they don't even consider it. And so hopefully with this module, they'll see that in the feature list, and then they'll start thinking, okay, well, I can use this. So it's yeah. So currently in the EAR SDK that everyone should have access to, there are 3 EIQ examples that make use of Neutron, with CFAR10, which is a simple image classifier, keyword spotting, and label image, which is more advanced image classifier model. Currently, these use static images preloaded into Flash, and they're only available at the moment in the MCX 9XX EVK SDK. So it's not in the 5XX or the breakout board SDKs, but that they will be eventually added to those boards as well. But just if you're looking for them, you got to make sure you're using the 9XX. There's also a face detection demo that some of you might have seen a video of or seen at your local event, because it's been going all over the China and the US and Europe. So this is a demo that's on the Nirvana breakout board, and I forgot to. So it's on the Nirvana breakout board. It uses a simple OV7670 camera, which you can get up really cheap off of Amazon for like $4. And it's using smart DMA to do the data transfers. And then there's a micro TFT passive LCD that's being controlled via FlexIO. Something I forgot to mention at the top is that you'll notice, you might recall from the Monday with the introduction, the MCX family does not really have LCD controller or camera controller or anything like that. And so there are ways, obviously, as seen here, to add camera and LCD support. but it's not inherently integrated in like it is on some of the i.MX RT devices. And also due to the relatively low amount of memory on these devices, it's also going to limit, what kind of models you can run. As I said before, the model optimization is getting better and better every day, but it is still going to be somewhat of a limiting factor. And so that's why we see a lot of we believe that there'll be more focus on things like anomaly detection for this particular device because of the lack of those features. But obviously, if a customer is interested, it can be run. That's why I have this demo. In a real world system, you probably don't even need the LCD because really that's just used for aiming the camera and seeing, making sure you're aiming at the right thing. But if you're integrated into a coffee maker or toaster or doorbell, then you're just using the camera. And so it's a bit more straightforward. So if anyone hasn't seen the demo, it's real quick, so I'll bring that up. Hopefully the sound will carry. I'm not sure it will, but you don't really need the sound. So this is what it looks like. Probably can't hear it, but it's just me saying this is a facial detection demo. And so we have a couple of these in Austin. So if you have an event, let us know. We can ship it to you to use for that event, or instructions on how to do your own once we have more breakout boards. But the China team did a lot of development with this to get this up and going real quick after we got the device. So it's very impressive. All right, so that then brings us to the benchmarking. So I'll let Rocky take over for this one and the work they've done on that.
Yes, thank you, Anthony. This is Rocky speaking. Can you hear me?
Yes.
Okay, thank you. So this is the benchmarking. There are 6 models getting benchmarked. The first 4 are coming from the MMPerf Tiny. This is a new inference benchmarking get adopted by multiple semiconductor for microcontrollers. And the 4 models can be on behalf of 4 typical use cases. The anomaly detection, it uses a neural network to identify anomalies in machine operating sounds. And the keyword spotting also use a neural network that detect audio keywords from a spectrogram. And the visual weak words, this is the portion imprecise binary classification and a small size image classification. We also have 2 live demos. The first one is the face detection, as Anthony just mentioned. And the image classification, we also make it live, and we can check the time. The time is measured, and the key takeaway is for the image classification and the image-related models. Neutron can, in fact, have about 40 to 50 times faster than the Codex M33 core at the same frequency, and about 5 or 6 times faster than the 600 MHz Codex M7. But for other models, such as the keyword spotting, it has the irregular convolution kernel size for the first layer. At that moment, getting benchmarked, it was not as efficient as the normal image classification kernels. And for the anomaly detection, there is no convolution kernel inside that model, and just use the fully connected. So there is only 1 out of 4 neutron calculation resource pipeline can be used. So the acceleration is not as much as the image-related AI workloads. And as for the energy savings, as the green date, you can see it is usually also more than 30 times faster and better for the Cortex-M core. And for the the other aspect about the RAM, this is not shown in this table, but from our benchmarking, it also saves a lot of RAM for image classification and for the larger image models, because the context parameters are become part of the weight and in the flash. But for the models running in ARM core, the quantization parameters must be decoded into RAM. So with Neutron, you can also save SRAM. Okay, and this is for this slide. That's Anthony. It can return to you.
All right. So that concludes the presentation. I haven't looked at the chat to see if there's any questions.
I think a number
Looks
of
like
them
there's
have
quite
been
a-
answered.
Okay, yeah, it looks like Rocky's doing a great job.
So one question I see toward the bottom is, do you have any plan to add to the EIQ portal the ability to work with audio files?
That is not on the roadmap at the moment. Obviously, that's always changeable, but at the moment, it's still focused just on image classification and object recognition images. And I will paste the camera and TFT into the chat here in a second. The models.
And then meanwhile, if anyone feels like their question wasn't answered in the chat or they have an additional question, please unmute your line.
And I see that there's a question about uploading different models for different tasks. And, Rocky mentioned that, yeah, you can. The real limiting factor there is just going to be a space of flash and RAM. But it's definitely possible.
I'm going to go ahead and stop the recording while you guys think of any final questions.